You're all set.
All right, well, thanks for having me. I'm going to talk about kind of using category theory with databases. And sometimes people think of databases as kind of the most mundane part of computer science, and category theory is kind of the heights of math or something like that. But in some sense, category theory is just designed to model some situation that you're interested in. It's a modeling language for math, and databases are to model some real-world situation oftentimes, and the flexibility that you want in both is actually pretty similar. So, well, I mean, the thing is, people hate databases in PL. Yes.
Would you be so kind as to move your mouse?
Oh, yeah.
Thank you.
Cool.
Not quite there. There you go.
Yes. All right.
Thank you.
Okay, sure. And so I want to make a clear connection between databases and categories to the extent that everyone here believes that they are very similar types of ideas, or almost the same thing in some ways. And to show some advantages of that connection, namely the conceptual clarity that category theory brings to a subject. A lot of times in database theory, there's kind of one central idea, which is the relation, and then everything else, foreign keys, queries, merging, and evolution, and all sorts of different problems that database people think about, and they're not really part of the main central theory, which is a little bit too easy. So I want to talk about how, if there's time, I don't know if I'll have an hour or not an hour, but anyway, if there's time, I want to talk about how you kind of convert between RDF and databases, and how that brings semi-structured data into kind of a relational style model, except with less. So how they can kind of play well together. To talk about functorial data migration. If you have two schemas, two database layouts, and you have a functor between them, then you can migrate data from one to the other in a functorial way. And to talk about views and queries, and then to talk about integration with programming language theory. Because the idea of the category of types and the way that categories work with databases are almost the same. And then just for today, I thought about monads, because people in Haskell like monads, so I thought about monads, and I'll talk about how they can, what they might possibly do in a database. You can tell me whether you think it's useful. Okay, so the basic idea is, think of a small category, and by small right now I actually mean finite category, as a database schema. And that a state or instance of that category is just going to be a functor, delta, maybe for data, taking C to set. And I'll go into how this is just an overview. But the power of this idea is its simplicity. I mean, if category and a schema are the same thing, database schema, then everything you know about categories you already know about database schemas, and vice versa. And set is the most basic category, so somehow functor to set is a very nice thing to want to do. By the way, the word functor in Haskell usually means a functor from Hask to Hask or something, whereas in category theory, of course, you can have a functor between any two categories. And again, I'll talk about that. Right, and this definition is easy, and its simplicity allows for a lot of theorems in category theory to go through, because there's not much being said here. And finally, it's self-contained, and so a lot of database theory fits inside without having to extend the model too much. So what's a category? A category models objects of a certain sort, like data types, and the relationships between them, like functions. This is a picture of a category that's a simple category. It always looks like a graph, but then there's a composition law saying I know what FG is and FH is. That's a new arrow in the category. And another way of saying it, or a way of implementing it, is to say that it's a graph, but I can declare two paths from A to B to be equivalent. So for example, I could say, this is my category, all the arrows are there, but I also want to say that if I do JK, that's the same as doing I 3 times. I can declare equivalences between two paths, and that gives you a category. So it's just a graph where you also consider paths, and you're allowed to say two paths are equivalent. But the formal definition is this. You need to give me a set of objects, between every two objects a set of arrows, and I'll draw, and I guess this is pretty self-explanatory notation for you guys, and a composition law. Given an arrow from X to Y and an arrow from Y to Z, you have to tell me what the composition is going to be. So in this previous example here, I really, for a category, need to throw in the composition of F and G, and the composition of F and H, and the composition of J and K, and JK, JK, J, and all that stuff. But there's something called a kind of a presentation of a category, where all you do is you give the graph and you give some equivalences, and that generates a category where where the only relations are the ones you've stated, and everything that they kind of generate. So anyway, these are what you need for a category, and they have to satisfy two laws. The identity law says that if I go from every object in your category has an identity arrow to itself, it says I am myself. If you do the identity arrow from X to X and then do F, that's the same thing as just doing F. And if you do F first and the identity on Y, it's the same thing as doing Y. And then this composition is associative, which is what allows me to talk about paths. That if I do F, then G, then H, if I compose F and G first, or G and H first, it's the same thing. It's just one path from beginning to end. So the basic idea is you can compose paths into an arrow. One basic example is the category of sets. It's maybe the most important. And an object in it is any set, and an arrow is a total function between two sets. And the composition law just takes two composable functions, A to B and B to C, and composes them. Okay, so that's an important category. So, all right. Any questions about categories? Yeah.
I'm not sure what a total function is.
Oh, a total function means every input has an output, as opposed to some inputs don't have output.
Function from math instead of function from computer science, where you could run forever. So
there's also a category where the objects are sets, but the morphisms or the arrows are partial functions. You compose to by saying that if something doesn't get the input of something.
partial functions suck.
Yeah.
Don't use them.
Okay.
Problem solved.
What's a functor? So I'm going to be talking about functors and categories a lot. And one way to think of a category, as I said, is a directed graph where certain paths have been declared equivalent. And a functor is a graph morphism, meaning that preserves these equivalences. So in other words, I have two graphs, nodes and edges, nodes and edges. For every node here, you need to give me a node there. For every edge connecting two nodes, you need to give me an edge connecting the two nodes over there. And if you have a path from A to B that's equivalent to another path from A to B, it should be equivalent on the other side as well. And I would want to note that the composition of two functors is a functor. Okay. So to recap, category system objects and arrows in a composition law. A functor is a mapping that preserves these structures. Set is the category whose objects are sets and arrows are these total functions. And so here's an example of a tiny category. It looks like a graph and there are no compositions to be set. There's nothing that's composable.
Identity
But over here, except for the identities. But over here I'm giving a functor from C to set. And so what that has to be is C has three objects, so this functor has to give me three objects in the category of sets. And the objects it gives me is this set, and that set. And my category C has two arrows, and so I need to give you two arrows in the category of sets. In other words, I need to give you two total functions. So given an input over here, I need to tell you what the output is, and I'll just send A1 to B1, A2 to B1, and A3 to B2. And this function is unique, like there's only one. And so this delta that I've drawn here is an example of one functor, but you can write down a million functors, one for every set A. So there's infinitely many functors from here to set. It's just three sets and two arrows between them. Okay, so then the question is, what's a database? At least, what's a database to me? Instead of its implementation, let's just think about what it's supposed to be. So it's supposed to be a bunch of tables and relationships between those tables. So the rows of a table are called records or tuples, and the columns of a table are called attributes. And every column in a database table is either pure data, like someone's first name, or it's what's called a foreign key or a primary key. Primary key just means it's kind of a reference for that row. And a foreign key means you look in some row and you look at the foreign key, and it sends you to another table and tells you what row to look in there. So if the US Postal Service has a table of addresses, and it's indexed by some primary key like 1173862, and that means 44 Windsor Drive, Cambridge, Massachusetts. I don't need to store 44 Windsor Drive. I can just point you to 116842. Yeah.
Two questions. Pure data. Do you mean flat data?
I mean literals? I don't know. I mean a string or int or float.
Okay. And why have you chosen to do this kind of more modern Ruby-ish approach of fixing an actual primary key column, say, rather than being all relational theory-ish and saying, the table's primary key is the things that, it's a relation. Its primary key is it.
Because in reality they tend to have row IDs or a set of unique identifiers. And second of all, I think that it works better mathematically. I don't like relations as much as I like categories. There is a category of relations, but it's very hard to deal with, actually. The category of sets is a much nicer one. And I think that the relational model is kind of based on a much older mathematical theory, that of relations and sets. Whereas this more categorical approach, which I'll show you in a second.
50 years older, or younger.
Yeah, 50 or 100 years younger, yeah. So, right. So the last thing I want to say is that a schema might have business rules, and this part is not in any relational model. You just kind of write a memo saying, the employee's manager's department is also the employee's department, or something like that. Okay, so here's an example that I just made up. And there's two tables, and what I want you to notice is that the manager of an employee is another employee. So David Hilbert's manager is Alan Turing, Bertrand Russell's is Bertrand Russell. So manager is a little better. So manager is a foreign key column back to employee, and DPT is a foreign key column to department. So everything in that column will be sending you to some row in that other table. Okay, so let me go into this part here. So here I'm just saying that these could just be row numbers or they could be typed. They're just different. They're similar. Either one's fine. And what I want to talk about is these business rules, the integrity constraints. Like the manager of an employee must be in the same department as that employee, or the secretary of every department, this is the foreign key back to employee. The secretary of every department must be in that department. You can make rules like that. But the last thing I want to say is here we have two data columns in employee and one data column in department, namely strings. But that technically you could also consider even a data column as a foreign key to a one-column table, kind of like a leaf in a graph. A one-column table where those are the primary keys. So I'm just sending you to the string, to the primary key DAVID, or BERTRAND. So even the data columns can be considered foreign keys. And the reason for doing that would be to kind of unify everything into one, unify the columns, unify everything into one interworking theory, where if later I wanted to say, I don't know, have a two-column table of integers and their parities, so 0, 1, 0, 1, or something like that, then I could still just extend my schema just a little bit and allow for, allow what used to be a pure data column to become something else. Or maybe it's not an integer anymore, but an integer between 0 and 10. I happen to know I want to kind of make a data abstraction